All right, here we go. So find the derivative of f of x equals log base e of modulus of x. Let's just break down some of this notation here. It's basically saying it's a function. So f is a function. The domain is all real numbers, not including zero. And the codomain is all real numbers. Don't worry too much about the codomain. It's always pretty much real numbers. And f of x equals log base e of modulus of x. If you're not sure what a real number is, I'll put a link down below to go watch a video about that. So let's jump into it. Basically, one thing you might think about is what is this modulus situation going on? Basically, this makes it what's called a hybrid function. So there's sort of two parts to it. So we've got a situation where x is going to be greater than zero and x less than zero. So let me show you what that looks like. There's basically two functions. The first part we can say, okay, let's call it sort of the first part, f1 of x is log base e of negative x for x values less than zero. And then we've got f2 of x equals log base e of x for x greater than zero. So let's look what that looks like. So it's going to look something like this. And maybe I'll just explain the reason that this is negative x. We can't take the log of a negative value, right? But if x itself is negative, and then we have a negative, it'll become positive overall. So log base e of modulus x is two parts, log base e of negative x and log base e of positive x. And this is what it looks like in green. So this is sort of a shorthand way of writing these two functions. I'll just point out as well that this first function is a reflection across the y-axis of log base e of x. Okay, so let's look at the derivative. I'm just going to give the game away. This is the graph of the derivative, which is this red line. And I'll show you why it's the derivative. So let's have a bit of a play around here. What we're going to do is we're going to draw a tangent on the green line. Then we're going to look at those values. So let's look. The gradient value at the moment, at this x value that it's at, is negative 0.09. And the y value of the red line is negative 0.09. So we can see that the y values of this red line are giving us the gradient values of the green line. So let's put it at another point maybe. And that's a bit hard to read there. But when the gradient is at this x value, the gradient is negative 0.29, y value negative 0.29. Okay, and then we get down to here and the gradient gets steeper. Okay, in this case, it's negative 5. The y value of this line is negative 5. Okay, obviously there's a point where it's through 0, where it doesn't, where it's undefined, because we can't include 0. So then we get to the right-hand side of the graph, and then similarly, we get the same situation going on over here. It's kind of visually what's going on. And you might be thinking to yourself, oh, I've seen this red line before. This red line is, in fact, the graph of 1 over x. So let's see if we can come to that conclusion by using some algebra. So let's just look at this first function for now. If we were to take the derivative of log base e of negative x, well, we could use the chain rule, couldn't we? We could say that negative x is the inner function and the outer function is log base e of u. So what we're going to say is y equals log base e of u. So if we take the derivative of log base e of u, we get 1 on u. Okay, and that's hopefully it doesn't seem like it's coming out of thin air. That is one of the rules you would have spoken about before, about the derivative of log e of x is 1 on x, or in our case now, the derivative of log e of u is 1 on u. Okay, so that means u is negative x. Okay, so the derivative of u with respect to x is negative 1. Differentiating this gives you negative 1. All right, applying the chain rule now, multiply this by this and sub u back in. So we get dy dx equals negative 1 multiplied by 1 on negative x, because u is negative x. So that gives you dy dx equals 1 on x. Okay, so that's good. So for this first part, we get that the derivative of it is 1 on x. Let's do the other part. Oops, let's do the other part here. So we know that for f1 of x, the derivative is 1 on x. And for the exact same reasoning, the derivative of the second part of the function for x greater than 0 is also 1 on x. So what we can say is that, yeah, for the derivative of this whole thing, therefore, is 1 on x, because the derivative of both parts of them is 1 1 on x. So we can just say, all right, the derivative of log base e of mod x is 1 on x. And, just to really make it clear with this green line to the right of x greater than 0 is the derivative of that is this right-hand part. Okay. And sort of what's going on the left is that, this green line to the left of 0, the derivative of that is also to the left of 0. So hopefully that sort of clarifies things for you a little bit, and you can sort of visually see why 1 on x is the derivative of log e of mod x. All right, let's try a problem. See if you can find the derivative of f of x equals log base e of sine x. So using very similar strategies to what we did before, see if you can come up with the derivative of this graph. It's a pretty funky looking graph, I would have thought as well. So by all means, go into GeoGebra, go into Desmos and graph the derivatives as well to see what it looks like. All right, good luck with your studies.